The signal arrived quietly, almost too quietly for something that would shake the foundations of modern cosmology. It was a whisper of ancient light, stretched thin by time itself, slipping into the instruments of the James Webb Space Telescope like an echo from a world that should not exist. Astronomers stared at the early data in silence, the faint glow registering as nothing more than a distant object. And yet, beneath that soft shimmer hid a contradiction so severe that it threatened to unravel decades of confident theories. The universe, it seemed, had decided to break its own rules, and to do so right in front of our newest and most powerful eye on the cosmos. At first glance, the signal looked unremarkable, the kind of dim speck that telescopes capture thousands of times a day. But something about it felt wrong. Light traveling across the universe carries fingerprints of its age, its distance, and the conditions of the space it crossed. And here, those fingerprints were out of place, as if someone had shuffled the chronological deck. Light this old wasn't supposed to come from something this bright, this massive, this structured. It was like finding the fossil of a fully grown tree inside a layer of rock formed before forests ever existed. In observatories around the world, scientists leaned closer to their screens, running simulations, recalibrating instruments, and questioning whether they were even reading the data correctly. But the deeper they looked, the stranger the picture became. The faint glimmer in JWST's field of view wasn't a mistake, it was a message. Something ancient, enormous, and impossible had formed in the infancy of the universe, long before any theory said it could. And it was shining straight at us. The tone in control rooms shifted from curiosity to unease. The early universe was supposed to be dark, chaotic, and slow. In the cosmic timeline, the first few 100 million years were thought to be a quiet dawn, a time when matter drifted aimlessly, gathering itself in fragile clusters, taking its first trembling steps toward forming stars. Galaxies shouldn't have existed yet. They needed time to grow, time to ignite, time to sculpt themselves into luminous islands of matter. But this object, whatever it was, had no regard for patience. It stood tall in an era where nothing of its scale should have stood at all. Some scientists tried to dismiss it. Perhaps it was a foreground object masquerading as something older. Perhaps an error in the redshift measurement tricked the system. Perhaps the calibration had been off by just enough to produce a cosmic illusion. But the more they tested these possibilities, the more they fell apart. The signal remained stubborn, persistent, and entirely incompatible with what the standard model of cosmology described. As the data spread through institutions, whispers turned into debates. Could this be an early supermassive galaxy? A hypercompact star cluster? Or something entirely new, something that had no name because no one had imagined it could exist? Every possibility felt like stepping deeper into a maze. No matter which path they took, they eventually hit the same wall. The universe was too young to produce what JWST was showing them. The emotional weight of the discovery grew. There was awe, certainly, a sense of wonder at witnessing something so ancient that it preceded even the earliest structures we believed could form. But there was also fear, the quiet kind that settles in when the ground beneath your understanding begins to crumble. If this object was real, and all evidence said it was, then the models that guided our view of the cosmos were incomplete at best, wrong at worst. And yet, the most unsettling part wasn't the object itself. It was the growing suspicion that this was not an isolated phenomenon. If one impossible signal had slipped through the veil of time, others might follow. The universe had offered its first anomaly, a single thread sticking out from the tightly woven tapestry of cosmology. Pull it, and the entire fabric might begin to unravel. The scene becomes almost cinematic. A dark control room, screens glowing with the ancient light of a world long gone, scientists staring at numbers that shouldn't exist, heartbeat moments where someone quietly mutters, "This can't be right," and another whispers back, "But it is." Outside, the night sky looks calm, serene, indifferent. But inside the data, a cosmic storm is building. This first signal is more than a discovery. It is a warning shot, a silent challenge from the universe itself. For decades, we believed we had traced the grand story of creation, how matter formed, how stars ignited, how galaxies assembled. But this tiny glimmer from the infancy of everything suggests that the story may be far more chaotic, far more rapid, and far more mysterious than we dared to imagine. And as astronomers prepare to investigate deeper, a haunting question begins to echo across research papers, conference halls, and midnight discussions. If the universe is revealing its secrets this quickly, what else has it been hiding just beyond our reach? In the vast silence of space, where distances grow so immense that even imagination begins to falter, the James Webb Space Telescope hovers like a lone lantern suspended over an ancient ocean. It is humanity's most ambitious attempt to pierce the darkness, to look not just outward but backward, toward the earliest chapters of existence. When we say JWST sees back in time, it sounds poetic, almost mystical, yet it is literal. Its mirrors drink in light so old that it began its journey before Earth existed, before the sun was born, before the Milky Way had even settled into its graceful spiral form. That ability alone gives JWST a kind of supernatural aura, as though it were less a machine and more a time traveler drifting through the void. To understand the magnitude of its power, imagine standing at the edge of a cliff and shouting into a canyon. Now imagine hearing not just your echo, but the echo of someone who shouted millions of years before you. Light works the same way. It carries memories, keeps secrets, and JWST is the first tool sensitive enough to catch the faintest of these ancient whispers. Photons stretched thin, pulled relentlessly across the expanding universe until they emerge not as visible light but as long, delicate waves of infrared. Ordinary telescopes cannot see such ghosts. They look at stars and galaxies in their current form, bright and well-defined. JWST sees their ancestors. To accomplish this, it needed eyes unlike anything ever built. Its primary mirror, gold-coated, honeycomb-like, shimmering with almost ceremonial beauty, collects light across a surface so perfectly aligned that even a shift smaller than the width of a human hair would blur the view. Behind it lie instruments capable of reading that light molecule by molecule, frequency by frequency, decoding not just what these objects look like, but what they're made of, how fast they're moving, even the age of the stars burning within them. It transforms the universe from a distant spectacle into a readable archive. Yet the true marvel lies not in the hardware but in the perspective it grants. For the first time we can gaze upon the universe when it was less than 1% of its current age, when chaos reigned, when the first atoms dared to gather, when gravity was still sculpting the earliest cosmic shapes. These are not just distant scenes. They are glimpses of a time so raw and volatile that it feels almost sacred, like peering into the moment before a story has learned how to tell itself. This unprecedented clarity is why the earliest JWST images stunned the world. They weren't just beautiful, they were unsettling. The deep fields revealed a universe far richer, far more crowded, far more structured than anything scientists predicted. Galaxies that should have taken billions of years to form appeared fully grown. Stars that should have sparked into existence slowly were blazing with impossible intensity. The cosmos, which theory described as slow and methodical, looked instead like a fast-moving storm. But before these mysteries erupted into scientific debates and cosmic panic, there was a quieter, more personal moment that every astronomer felt. The realization that they were witnessing light older than everything they knew. That the glow before them was not merely distant. It was ancient, a relic from the universe's childhood, a souvenir from a time before time had meaning. Standing in front of these images, even seasoned researchers experienced a strange sensation, as though the telescope had peeled away the present and exposed something primordial. Some described it as awe, others as discomfort. Because with such clarity came a revelation. The more we see, the more we realize how little we understand. This duality, wonder and fear, defines the emotional core of JWST's mission. On the one hand, it fulfills humanity's deepest curiosity, to know where we come from, how the cosmos built itself, how the first sparks of structure ignited in the darkness. On the other hand, it challenges our intellectual pride. The universe, revealed in such intimate detail, seems to be telling us that our theories are tentative sketches, fragile interpretations of a reality far more complex than we imagined. As JWST captures more data, its role becomes almost philosophical. It forces us to confront the limitations of human perception. For centuries we believed we understood the cosmos because we could observe its surface, its stars, its motions, its patterns. But infrared vision reveals the hidden scaffolding beneath that surface. It shows the dust clouds where stars are born, the faint filaments connecting galaxies, the invisible structures shaping matter on the grandest scales. It unveils the skeleton of the universe. And the deeper it looks, the more the narrative shifts. Instead of a calm, steadily evolving cosmos, JWST shows an early universe bustling with activity, filled with objects far too mature for their age. It is as if someone opened a history book expecting primitive cave paintings and instead found fully developed cities carved into stone. The timeline breaks. The logic phrase, something is off. This realization marks a turning point, not just in astronomy but in our relationship with the unknown. Because if JWST can reveal galaxies that shouldn't exist, what else might it uncover? Are there phenomena so bizarre, so contrary to our understanding, that we haven't even named the concepts needed to describe them? JWST's eyes may be mechanical, but the questions they force us to ask are deeply human. As the telescope continues its silent watch, drifting far from Earth, it becomes a symbol of a growing tension between expectation and discovery. Scientists hoped it would confirm their theories, polish them, refine them. Instead, it is tearing holes in the story, exposing gaps wide enough to swallow entire models. Its golden mirrors reflect not just starlight but uncertainty. And yet, this uncertainty is thrilling. It is the engine of progress, the spark that ignites revolutions in thought. JWST isn't simply showing us the past, it is showing us the future of science, a future where the universe is stranger, faster, and more creative than our most confident equations allow. The telescope's gift is not just sight. It is perspective. And perspective, especially on a cosmic scale, changes everything. JWST is rewriting the boundaries of what is possible. It is revealing a universe still full of surprises. And as we stare into the deep fields, mesmerized by the ancient light pouring into our instruments, one question pulses at the edge of every discovery. If this is what we can see now, what else has been waiting for us in the darkness? It appeared first as a tiny point of light, something so unassuming that an untrained eye might have scrolled past it without a second thought. But astronomers trained to read the universe like a language felt an instant jolt. That faint dot was not faint at all. It was simply far away, so far that the light had traveled almost the entire age of the universe just to reach JWST's mirror. And when its redshift value was calculated, the mood in the room changed. This wasn't a typical early galaxy. This wasn't even an unusually early one. It fell into a category scientists never expected. It was impossible. A galaxy too massive, too bright, and too well-structured to exist at such an astonishingly young cosmic age. The shock hit like a tidal wave. To understand why it caused such turmoil, imagine the early universe as a cooling forge. Matter was still spreading, gravity still gathering, stars only beginning to flicker into existence. In those first few 100 million years, everything should have been simple, sparse, clumpy, and chaotic. For a galaxy to exist at that time, it would need stars, dust, heavy elements, and the gravitational scaffolding to bind them together. That takes time, millions upon millions of years. And yet, the light captured by JWST told a completely different story. This galaxy had not only formed but matured long before the universe had any right to produce such complexity. When the properties of the object were analyzed, the disbelief deepened. Its estimated mass wasn't the mass of a tiny proto-galaxy. It was hundreds of millions, possibly billions of solar masses, enough to rival modern galaxies that had billions of years to evolve. It emitted the kind of luminosity associated with large populations of stars, not the small, primitive clusters expected from the cosmic dawn. Its structure suggested rapid organization. Its brightness implied intense star formation. Every metric contradicted theory. It was like discovering a fully developed metropolis in a region where one expected scattered tents and fire pits. Researchers repeated the calculations, combed through the data, and even checked software for errors. But every verification strengthened the same conclusion. This galaxy wasn't supposed to be there. It was too big for its era, too brilliant for the timeline, too evolved for the conditions of the early cosmos. Something fundamental was wrong, not with the telescope but with humanity's understanding of how galaxies form. This first impossible galaxy sparked equal parts awe and dread. Astronomers had long predicted the existence of early galaxies, but they were expected to be small, dim, and fragile. This was none of those things. It stood defiantly against every model of cosmic evolution, against every assumption about the slow rise of structure after the Big Bang. That defiance made it irresistible. Scientists leaned into the mystery, drawn to it like moths to a flame, even as the implications began to unsettle them. The discussions grew intense. Some argued that perhaps the galaxy wasn't as massive as it looked. Maybe stellar populations behaved differently in the early universe, making the object appear heavier than it truly was. Others suggested exotic star types, supermassive stars or unusual distributions of stellar masses that could boost brightness. Yet even those explanations failed to capture the scale of the anomaly. The numbers simply refused to fit within the boundaries of known physics. The galaxy wasn't merely surprising, it was defiant. More troubling was the timeline. For this galaxy to exist at such an early epoch, star formation would have needed to begin almost immediately after the Big Bang. But the universe didn't allow that. Before stars could form, atoms had to cool, gravity had to start gathering matter, and the first dark matter halos had to settle into place. This process should have taken hundreds of millions of years. Yet the galaxy's age implied that star formation began with startling speed, almost as if the universe rushed to structure itself faster than any model predicted. The more astronomers examined the galaxy, the more questions emerged. Had matter clumped together more efficiently in the early universe than previously thought? Were the first stars far larger, brighter, and shorter-lived, producing heavy elements at an accelerated pace? Did dark matter play a more active, aggressive role in shaping early structures? Or was something even more dramatic happening, something that challenged the very fabric of cosmology? Some scientists began quietly proposing reforms to the entire model of galaxy formation. Perhaps the universe was more productive in its early stages. Perhaps the first gravitational wells formed far earlier. Perhaps the cosmic timeline needed to be stretched or reshaped. But these suggestions came with heavy consequences. If the models changed, countless predictions about cosmic evolution would need rewriting. The foundations of astrophysics would need reinforcement. And confidence in long-held theories would crumble. But the true turning point came when researchers asked a simple question. What if this wasn't an isolated case? One impossible object might be a fluke, a cosmic coincidence. But if more appeared, if this galaxy had siblings lurking in the shadows of the early universe, then the anomaly wasn't just a puzzle. It was a warning. As more deep-field images were processed, hints of other bright objects began emerging. The realization set in like a slow, cold wave. This might be the first of many. A pioneer of the impossible. A beacon signaling that the universe's early history was far richer, far faster, and far stranger than anyone had anticipated. The philosophical weight of the discovery was equally profound. Humanity had always viewed the cosmos as a place governed by elegant rules, rules we believed we were steadily decoding. But this galaxy mocked that confidence. It suggested that the universe was capable of surprises so vast that even our most advanced theories barely scratched the surface of truth. It forced scientists to confront the possibility that the cosmic dawn was not a gentle, gradual beginning, but a roaring storm of creation, violent, accelerated, and deeply enigmatic. And as researchers stared at the image of this ancient giant, a bright smear of light older than almost everything else, they felt a mix of emotions difficult to describe. Awe at its existence, fear at what it implied, curiosity burning hotter than ever. Because in that small, distant glow lay a message the universe had kept hidden for nearly its entire lifetime. A message that said, "You do not yet understand me." This first impossible galaxy was more than a discovery. It was a declaration. A cosmic challenge. And as JWST prepared to look deeper, astronomers braced themselves for the possibility that the universe had only begun to reveal how strange it truly was. When the first impossible galaxy emerged from JWST's early data, astronomers treated it like an outlier, a strange cosmic glitch, remarkable but isolated. Yet the universe rarely delivers mysteries one at a time. As researchers widened their search, they began to spot patterns lurking behind the darkness like silhouettes. When the first impossible galaxy emerged from JWST's early data, astronomers treated it like an outlier, a strange cosmic glitch, remarkable but isolated. Yet the universe rarely delivers mysteries one at a time. As researchers widened their search, they began to spot patterns lurking behind the darkness like silhouettes waiting to be illuminated. One by one, additional galaxies appeared, each carrying the same unsettling signature. Too massive, too luminous, and too mature for their place in the timeline. The anomaly was multiplying. With every new detection, the tension grew. These weren't minor deviations from expectation but bold violations, like students turning in entire novels when assigned their first paragraphs. Galaxies in the early universe were supposed to resemble messy drafts, brief, chaotic, incomplete. But JWST was showing polished structures, shaped with surprising precision. Even after rigorous data checks, the story refused to change. The universe, in its infancy, seemed to be operating on fast forward. The scientific community responded with a mix of excitement and disbelief. If a single impossible galaxy forced a re-evaluation of cosmic history, a collection of them demanded something far more drastic, a potential rewriting of the foundational frameworks that govern cosmology. Researchers began searching for patterns, similarities in size, brightness, formation rates. What they found was unsettling. These galaxies did not merely break the rules, they broke them in the same way, as though following a blueprint beyond human understanding. Some suggested that perhaps the earliest galaxies formed through mechanisms not yet imagined, processes far more efficient than current models allowed. Maybe the first stars were capable of seeding galaxies at breathtaking speeds. Maybe dark matter halos collapsed more aggressively. Maybe the cosmic environment in those first few 100 million years was a furnace of creation rather than a gentle simmer. Theories multiplied, but none explained everything. As debates intensified, a philosophical question hovered in the background. What if the textbooks had conditioned scientists to expect simplicity where the universe had always been chaotic? Traditional models described early cosmic structure as fragile, slow-building, almost timid. But what if the first epoch was instead a cosmic wildfire? The new data suggested a universe that didn't ease into existence. It erupted. And that eruption left behind structures so advanced that even the most open-minded researchers struggled to comprehend them. Yet the anomalies shared another strange characteristic. Their distribution across the early universe did not appear random. They clustered in certain regions of the deep field images, like islands rising from a turbulent sea. This pattern hinted at some deeper organizing principle, perhaps a hidden variable shaping the early cosmos. Something that pulled matter together faster, ignited stars earlier, or structured galaxies more aggressively than gravity alone could achieve. Scientists scrutinized the data, wondering if a new force or unknown property of spacetime might be at play. As these possibilities emerged, so did a growing sense of awe. The universe seemed to be revealing a secret that had been locked away for 13 billion years, and JWST had become the key. Each new discovery added weight to the suspicion that the earliest chapters of cosmic history were far more eventful than previously believed. Instead of a dim, wandering infancy, the universe's beginning appeared vibrant and restless, filled with hidden architecture waiting to be uncovered. But not all scientists were comfortable embracing such radical interpretations. Some clung to the hope that measurement errors or misinterpretations of infrared signals might explain away the anomalies. Others questioned whether unknown dust properties could be tricking the telescope into overestimating mass. And yet, every attempt to simplify the mystery seemed to collapse under scrutiny. The data was stubborn. The patterns were consistent. The early universe had secrets, and it was done hiding them. Meanwhile, the emotional landscape of astronomy shifted. Researchers accustomed to steady, incremental progress found themselves facing a storm of contradictions. For some, the thrill of discovery outweighed the discomfort of uncertainty. For others, the erosion of trusted models felt like losing the foundation beneath their intellectual footing. The universe had always been strange, but this level of strangeness forced a reckoning. It demanded humility. It demanded courage. It demanded imagination. With each new observation, a deeper fear began to take shape. What if our theories had been limited not by lack of data but by lack of vision? What if the early universe was never meant to fit neatly into our equations? These questions lingered in conference halls, in midnight emails, in long, silent moments of contemplation. The cosmos, once thought predictable, was revealing a wilder personality, one that refused to remain within the boundaries humans had drawn for it. The section ends at a crossroads. Scientists stand before a growing pattern of impossible galaxies, each a crack in the structure of cosmic theory. The familiar map of the universe is beginning to warp, its lines bending under the weight of new discoveries. And as the anomalies multiply, a haunting question grows louder. If so many early galaxies defy explanation, then what force sculpted the cosmos into these impossible shapes? The temperature in the room seemed to drop as the implication took hold. Was this structure a relic? A phenomenon? A fluke of cosmic evolution? Or was it something far older and more deliberate than any human mind could conceive? No one dared voice the question aloud, yet it reverberated unspoken among them, a silent tremor of possibility and fear. Then, without warning, the brightness of the object surged. Not dramatically, just enough for the change to be unmistakable. The monitors refreshed, recalibrated, and displayed the updated luminosity curves. The spike was brief but significant. Objects at that distance did not fluctuate so quickly, certainly not without an external catalyst. The team scrambled to interpret the change, arguing in hushed tones about stellar remnants, gravitational lensing, or unknown energetic events. None of the theories fit. The brightness surge did not follow the signature of any astrophysical mechanism. It looked more like a heartbeat, a quiet, rhythmic pulse that seemed to emanate from the structure itself. The idea was outrageous, yet the data refused to comply with conventional explanations. The room filled with a rising energy, a mix of wonder and panic, as though they were witnessing a cosmic giant stirring from its slumber. As the final set of diagnostics completed, a stark realization emerged. The object did not match anything in the known universe. Not even close. Its spectrum, geometry, luminosity, and energy distribution placed it outside every theoretical framework the team possessed. The discovery was not simply unexpected, it was impossible. The realization left a void of silence in the room, an eerie stillness broken only by the faint ticking of a wall clock. Time felt distorted, stretched thin by the enormity of what lay before them. Dr. Hale exhaled slowly, feeling the weight of a truth too vast to articulate. They had crossed a threshold tonight, one from which there was no return. Whatever the universe had chosen to reveal, it was something that defied understanding and demanded a new way of seeing. The night of detection had become the night reality shifted. The researchers gathered closer still, forming a tight circle around the primary display as though proximity might grant clarity. But clarity did not come. Instead, the object seemed to grow stranger the longer they examined it. Patterns emerged only to dissolve, symmetries aligned only to fracture into impossibility. It was as if the structure existed in a state of shifting identity, revealing different truths depending on the angle of observation. Theories flew across the room, quantum-scale anomalies scaled to cosmic proportions, remnants of a universe before the Big Bang, or a phenomenon birthed in dimensions humanity had no language for. Every idea felt simultaneously profound and inadequate. The sense of standing at the edge of comprehension tightened around them, a reminder that the cosmos was under no obligation to be understandable. As the clock crept past midnight, exhaustion mixed with adrenaline, but no one considered leaving. The monitors glowed like a constellation of artificial stars, illuminating faces filled with awe and fear in equal measure. The anomaly held their attention with effortless gravity, a silent declaration that the universe still guarded secrets powerful enough to unmake certainty itself. Even in their fatigue, the researchers sensed that this discovery marked the beginning of something vast and transformative. The anomaly was not just a scientific puzzle. It was a threshold, a doorway into a realm of understanding humanity had never stepped into before. And as the night deepened, one unsettling truth became impossible to ignore. In the earliest ages of the cosmos, when reality itself had barely begun to take shape, the universe existed in a state so dense and chaotic that even the simplest movements of particles carried the weight of unimaginable energy. Light, which we now treat as the most familiar messenger of the universe, had to push its way through a turbulent ocean of plasma, colliding constantly with electrons, protons, and pockets of early matter. The photons that now arrive in JWST's instruments began their journey in a world that would feel alien to us, a realm where temperature, density, and time all behaved according to rules unlike anything that governs the later universe. Yet despite that alien environment, those photons preserved traces of their origin. And it was precisely those traces that left scientists stunned when the JWST began delivering its earliest deep-field images. The mystery did not lie only in the galaxies themselves but in the timing of the light they emitted. Photons arrived from an era so close to the Big Bang that their very existence seemed contradictory. It was not simply that the galaxies looked older than expected, it was that the timeline implied by the photons themselves did not align with the universe's age at the moment they were released. These photons carried signatures that required long periods of cosmic evolution, cycles of star formation, the explosions of massive stars, the dispersal of heavy elements, and the assembly of complex galactic structures. Yet those processes should have taken hundreds of millions of years. The problem was simple and devastating. The light that JWST received did not belong to a universe old enough to have created it. Astronomers initially suspected measurement errors. Maybe the redshift values had been misinterpreted. Maybe gravitational lensing had altered the readings. But the more they checked, the more consistent the data became. The spectral fingerprints of these galaxies were unmistakable. Heavy elements like oxygen, carbon, and even neon, materials that required generations of stars to form, were present far earlier than the cosmic timeline allowed. For such elements to exist, an even older population of stars must have lived and died before them, enriching the surrounding gas. Yet the universe, based on all known physics, simply had not existed long enough for such cycles to occur. This contradiction created a mental divide among scientists. On one side were those who believed the data suggested extremely rapid formation mechanisms. Maybe the early universe was far more efficient at forming stars. Maybe primordial clouds cooled at unprecedented rates, collapsing into massive stars in a fraction of the expected time. On the other side were those who suspected something deeper. Not just a correction to the timeline, but a flaw in the very way we understand the unfolding of time after the Big Bang. The idea was unsettling. Light, which has always been treated as the most trustworthy witness of cosmic history, appeared to be reporting events that should not have been possible. The paradox felt like a form of cosmic vertigo. If the photons were authentic, and they were, then something fundamental about the early universe's behavior did not match our equations. And yet physics teaches that light cannot forge its own history. It carries the imprint of its origin faithfully, preserving the memory of temperature, composition, and chemical conditions at the moment of its creation. Light does not lie. Therefore, the only conclusion was that something in our understanding was incomplete. As JWST continued its observations, more galaxies appeared exhibiting the same troubling characteristics. Compact structures with masses far larger than expected, star populations too mature for their supposed age, and chemical signatures indicating multiple generations of stellar evolution. Each discovery added weight to the growing suspicion that the cosmic dawn was not the slow, dim phase astronomers had imagined but an era of explosive creativity, where the universe seemed to leap forward in complexity. Some scientists proposed that dark matter played a larger and more active role than previously believed. Perhaps dark matter halos formed earlier and faster, creating gravitational wells that accelerated the collapse of baryonic matter. Others speculated that early stars were far more massive, burning through their life cycles quickly and producing heavy elements at a pace modern stars could never match. These ideas provided partial explanations but never fully addressed the timing problem. Even if early stars formed quickly, the universe still needed time for them to live, die, and spread their elements into new generations. More radical theories explored the possibility that spacetime itself behaved differently near the beginning. Maybe time passed at varying rates depending on density or curvature. Perhaps inflation created localized pockets where cosmic evolution unfolded faster. These bold hypotheses attempted to reconcile the mismatch between observation and theory, but each one raised further questions. If time flowed differently in the early universe, how would that affect the rest of cosmic history? Would the universe have experienced different temporal speeds in different regions? And if so, why do we not see evidence of such distortions in later eras? As the debate grew, the emotional weight on the scientific community intensified. Many astronomers had built their careers on carefully refined models of cosmic evolution. Their equations had predicted galaxy formation with remarkable accuracy, until JWST arrived and revealed the universe's earliest chapters in far greater detail. Familiar landmarks dissolved. The tidy timeline of cosmic history, once considered well understood, now appeared full of shortcuts, leaps, and contradictions. The more they studied the data, the more it seemed the early universe was not merely faster but fundamentally different. The cosmic dawn looked turbulent, efficient, and strangely advanced. Galaxies did not form gently but erupted into existence, built by mechanisms still unknown. And yet, these mechanisms left behind clues in the form of light that had traveled billions of years to reach us. Light that insisted something extraordinary happened in those first few 100 million years. The most unsettling part of the mystery was not the galaxies themselves but the questions they raised. If light is the most honest storyteller the universe offers, and its testimony contradicts our understanding, then the error lies not in the light but in our interpretation of time. The photons whisper a possibility scientists are only beginning to confront, that the early universe may have experienced phases where time, expansion, and structure formation did not obey the rules that govern the later cosmos. As JWST continues to expose the hidden depths of the ancient universe, one question looms larger than all the others, a question both simple and profound. What unfolded in those first moments after the Big Bang that allowed light to reach us too soon? If you want Section 6 next, just tell me the word count. In research centers across the world, the first whispers began as casual doubts, tiny cracks forming in a structure that had appeared unshakable for decades. At first, no one wanted to say it out loud. There was too much history behind the models, too much confidence built over generations of cosmologists who believed they had mapped the universe's earliest stages with near-surgical precision. But when the JWST deep field images arrived, the silence in those rooms felt heavier than any equation ever written. Scientists stared at data that contradicted the very foundations of their understanding, and suddenly, the universe looked less like a well-behaved system and more like a puzzle missing half its pieces. The discomfort spread slowly, an unease that sat in the mind like a dim light flickering at the edge of vision. Researchers who had spent their lives defending the lambda-CDM model, the reigning framework of cosmology, now found themselves re-examining its assumptions with trembling skepticism. They watched as observed galaxy masses exceeded predictions by factors of 10, sometimes more. They saw star formation rates that felt impossible for the cosmic age. They measured chemical signatures that shouldn't have existed for hundreds of millions of years. And for the first time, cracks began to appear not in the data, but in the theories that had once shaped the data's meaning. Some tried to hold the line. They argued for calibration errors, unusual gravitational lensing, or rare outliers. But the outliers kept multiplying. Every new JWST observation felt like a blow to the ribs of the old model, each one tearing another thread from a tapestry that had hung proudly in every university lecture hall. The community found itself in a strange emotional space, half exhilaration, half dread, because they were watching the collapse of a story they thought was complete. The imagery that circulated in cosmology forums became symbolic. Diagrams of expanding spacetime now intersected with red, jagged lines indicating model deviation. It was as if the mathematical universe, the clean one that lived in equations and simulations, had begun to crumble from within. The metaphor of collapsing structures became unavoidable. An entire intellectual architecture, carefully built, passionately defended, was beginning to tilt. Some researchers took to describing the moment as a kind of cosmic betrayal. For decades, the universe had behaved according to the rules humans assigned to it. It had matched predictions with almost suspicious consistency. CMB readings, galaxy distributions, expansion curves, the data had always cooperated. But now it felt like the universe had simply decided to stop playing along. The deeper JWST looked, the stranger reality became, as if the cosmos were revealing a hidden complexity it had kept concealed until humanity developed a telescope powerful enough to force the truth into view. In conference rooms, the tension was palpable. Presenters would show slides with impossible galaxy masses and then pause, silently acknowledging the discomfort of the room. Senior physicists leaned forward with furrowed brows, while younger scientists exchanged cautious glances, unsure whether they were witnessing the end of an era or the beginning of a scientific revolution. Every question felt sharper. Every assumption felt newly fragile. Some theorists clung to the idea that early star formation might have been wildly more efficient than models assumed. Others suggested exotic cooling mechanisms or unknown interactions in primordial gas clouds. But each explanation felt like patchwork, temporary fixes on a foundation beginning to buckle. The more they tried to force the old model to accommodate the new data, the more the contradictions grew. It was here that a darker possibility began to emerge. What if the issue wasn't the galaxies at all? What if the real problem lay in how fundamental forces behaved in the early universe? Researchers revisited equations describing gravity at cosmic scales, examining whether the familiar force that shaped stars, planets, and galaxies might have acted differently under the extreme conditions near the dawn of time. The suggestion was almost taboo. Gravity, Newton's ancient companion, Einstein's masterpiece, the quiet architect of the universe, had been treated as one of the few certainties in cosmology. To question it felt like questioning the ground beneath one's feet. And yet, murmurs of modified gravity, early universe variations in gravitational strength, and even time-dependent gravitational effects began slipping into discussions that once would have dismissed such ideas outright. The emotional weight of this realization was immense. If gravity itself behaved differently in those early epochs, then everything built upon our understanding of cosmic evolution would need to be reworked. The neat sequence of events, from the first atoms to the first stars, from stars to galaxies, from galaxies to clusters, would need to be redrawn from scratch. Theories that had survived decades of scrutiny could unravel in a matter of months. Scientists found themselves standing at the edge of an intellectual cliff, looking down at a landscape where the rules of physics might not have been uniform across time. And once that possibility entered the room, it refused to leave. It spread through discussions like a cold draft, subtle but impossible to ignore. Outside the labs, the night sky remained serenely unchanged, stars glimmering with the same silent patience as always. But inside the scientific world, the consensus that once felt solid began to dissolve. Theories that had explained so much suddenly explained too little. And with every new JWST observation, the cracks in the old story widened. The moment of fracture became undeniable. The universe wasn't behaving according to the script scientists had written for it. Something fundamental wasn't just bending, it was breaking. And as researchers stared deeper into the strange ancient light, one unsettling possibility lingered like a shadow at the edge of the cosmos. Gravity, the force that shapes everything, may not act the way we think it does. In the early days after the JWST's first revelations, scientists clung to one desperate hope: that the galaxies appearing impossibly mature were rare exceptions, statistical anomalies that would vanish once a broader survey was taken. But as the telescope continued to pierce deeper into the primordial darkness, the opposite happened. The anomalies multiplied. The early universe, supposed to be slow, clumpy, chaotic, and barely organized, looked astonishingly productive. It was as if the cosmos had been running on an accelerated schedule, assembling massive galaxies while the universe was still in its infancy. And this forced researchers to confront a question that felt like an intrusion into sacred territory. What if the universe builds structure faster than it expands? Observations showed galaxies with more stars than entire modern clusters, packed into regions too compact to reconcile with standard formation timelines. Some formed stars at rates hundreds of times faster than the Milky Way, yet they existed when the universe was still a toddler, only a few 100 million years old. These galaxies glowed with the fierce blue light of newborn stars, but their chemical signatures hinted at ancestors, older stars that must have lived and died before them. That implied an even earlier era of cosmic creativity, one for which no model accounted. What made the universe so efficient at creating complexity so quickly? The contradiction felt like watching a sapling grow into a towering tree overnight. Astronomers compared the phenomenon to a cosmic assembly line operating at breakneck speed, producing stars and heavy elements in quantities that should have taken many billions of years. Gas clouds collapsed into dense structures far too rapidly. Supernova cycles appeared to have churned through generations at impossible speeds. Either the universe had been extraordinarily fertile in its youth or something fundamental, perhaps something never before imagined, was accelerating the process behind the scenes. Researchers began to explore every possible mechanism. Some proposed that primordial gas clouds cooled at unprecedented rates due to exotic interactions in the early plasma. Others suggested dark turbulence within dark matter halos, an unknown effect that compressed matter more efficiently. A few theorists speculated that the earliest stars, population 3 giants, might have been so massive, so volatile, and so numerous that they injected enormous energy into their surroundings, catalyzing rapid formation cycles. These stars, burning with unimaginable fury, could have lived short lives that seeded future generations with elements needed for faster development. But even these bold ideas fell short. The galaxies were still too large, too heavy, too chemically advanced. The models still underestimated their masses by orders of magnitude. They still required time that simply did not exist. The mystery deepened when simulations attempted to recreate the early universe with accelerated conditions. Even when parameters were pushed to extremes, denser initial gas, stronger gravitational collapse, faster star formation, the results still lagged behind JWST observations. Every simulated universe built structures too slowly. Every calculation showed deficits where the real universe showed abundance. The cosmos was outperforming even the most imaginative theoretical scenarios. It was as if reality itself were cheating. This led to one of the most unsettling discussions in modern cosmology. Perhaps the universe has a natural tendency toward structure, an innate drive toward complexity that scientific models have underestimated. Instead of being a passive environment shaped only by gravity and thermodynamics, the early universe might have been an active, dynamic arena with processes optimized for rapid creation. That possibility blurred the line between physics and philosophy, forcing researchers to reconsider their assumptions about what the universe should do. Some physicists proposed a radical idea. What if expansion and structure formation were not independent? What if, in certain epochs, the universe prioritized building over stretching? In that scenario, pockets of matter could form galaxies faster than expansion diluted them. The concept felt heretical, contradicting decades of cosmological orthodoxy. Yet the data demanded explanations that went beyond comfortable boundaries. The imagery emerging from this debate was striking. Scenes of a universe igniting with creative force, assembling stars and galaxies with a determination that defied logic. The early cosmos became a stage of furious activity. Collapsing clouds, racing photons, explosive stellar births. It was not a calm beginning but a cinematic eruption of order rising from chaos. And beneath the excitement lurked a quieter, deeper fear. If the universe was too good at making galaxies early on, what else had it been hiding? What other processes might be operating under the surface? Processes invisible to our instruments, detectable only through their consequences. The question took root in every cosmologist's mind. What if these early giants were not outliers but indicators of a cosmic principle we still do not understand? What if nature itself has a bias toward complexity, a hidden acceleration woven into the fabric of spacetime? The more scientists studied the data, the more the question sharpened. The universe wasn't just efficient, it was suspiciously efficient. So efficient, in fact, that it seemed almost intentional. The section closed on a thought that unsettled even the most rational minds. The universe might not only expand, it might build. And if that is true, then everything we know about cosmic evolution from the first stars to the last galaxies must be reimagined from the ground up. They had always called it the universe's hidden scaffolding, an invisible lattice woven through space, guiding the formation of galaxies like a silent architect. Dark matter had been the most trusted explanation for cosmic structure for nearly half a century. It explained rotation curves, gravitational lensing, and the large-scale web stretching across the cosmos. But as JWST pushed deeper than any instrument before it, that trust began to fracture. Something about the unseen architect no longer fit the blueprints. The galaxies JWST revealed were simply too massive, too early, too organized. And if the galaxies were wrong, then the ghostly framework that supposedly shaped them was wrong too. Dark matter became the prime suspect not because it was visible, but because it wasn't. It had always been a placeholder, an elegant patch that fixed equations without truly explaining the mechanism. For decades, scientists accepted it because it worked, because it behaved predictably, because it made models align with observations. But now those models were misaligned by catastrophic margins. Dark matter halos were supposed to form gradually, clustering first in small knots, slowly merging into larger structures. Instead, JWST was showing enormous halos, or something that behaved like them, already present when the universe was barely out of its primordial fog. The inconsistencies grew sharper with every measurement. Galaxy masses suggested that their dark matter halos must have been unbelievably large, but the timeline left no room for such halos to form. It would be like discovering a city with skyscrapers but no record of its foundations ever being laid. Something essential was missing. Something was off in the darkness. Astronomers began to question the very nature of dark matter. Was it truly cold? Was it collisionless? Was it even matter in the traditional sense? Some wondered whether dark matter particles might interact with themselves in ways previously undetected, creating dense cores far earlier than expected. Others hypothesized more exotic behavior, fluid-like dark matter, wave-like dark matter that clumped and condensed through unknown forces. But each explanation felt like grasping at shadows. They provided possibilities, not clarity. The emotional tension rose as cosmologists realized they were turning their doubts toward the core of modern astrophysics. Dark matter wasn't just another ingredient in the universe, it was the ingredient. Roughly 85% of all matter was believed to be dark. If its role was misunderstood, then everything downstream, galaxy formation, cosmic structure, gravitational interactions, would have to be reinterpreted. The universe's skeletal framework was no longer reliable. The invisible map guiding billions of simulations and research papers suddenly felt like a smudge on glass rather than a clear outline. A wave of unsettling analogies entered scientific discussion. Some described dark matter as a ghost whose footsteps no longer matched the floorboards. Others compared it to a puppeteer pulling strings in a pattern that seemed, at last, incoherent. And then came the analogy that stuck. Dark matter was like a master builder who had followed a different set of blueprints than the one scientists assumed. One of the most troubling discoveries came from gravitational lensing data. Some early galaxies bent light more strongly than their visible mass allowed, indicating an abundance of dark matter, but in configurations never predicted by simulations. These halos were not smooth, spherical envelopes but jagged, uneven anomalies as if shaped by forces unknown. In several cases, the inferred dark matter distribution was so strange that researchers questioned whether they were witnessing a different phenomenon entirely. Whispers of a radical idea resurfaced. What if dark matter wasn't matter at all, but the result of modified gravity or another effect we had misinterpreted? For years, alternative theories had been dismissed as fringe, monde, emergent gravity, or hybrid models where the force of gravity behaved differently at cosmic scales. JWST's revelations dragged these controversial ideas back into the spotlight. If the anomalies persisted, if the dark matter framework failed in the earliest epochs, then perhaps the universe wasn't hiding something invisible, perhaps physicists simply misunderstood how gravity behaved across vast distances and times. The debates became heated. Entire careers had been built on dark matter. Researchers who once mocked modified gravity now found themselves rereading papers they had ignored. Conferences turned into battlegrounds where equations were weapons and simulations became shields. No one wanted to abandon dark matter. It had been too successful, too elegant. And yet, the early universe was refusing to cooperate. At the same time, another unsettling possibility emerged. Maybe dark matter existed, but not in the form scientists had imagined. Some theorists began speaking in near-whispered tones about the dark sector, a hypothetical realm containing multiple kinds of dark particles interacting through their own version of forces, a shadow physics parallel to our own. If true, then dark matter halos might have evolved rapidly through interactions completely invisible to our detectors. A dark universe within the universe, a realm shaping ours from behind a veil. This idea was terrifying and thrilling. It suggested an entire hidden history unfolding alongside the visible cosmos, a narrative we could observe only through faint gravitational echoes. If dark matter had its own physics, its own interactions, its own internal dramas, then human understanding of the universe was painfully incomplete. As the scientific community wrestled with these possibilities, a darker thought began to circulate. What if dark matter had misled them from the beginning? What if the elegant solutions it provided were only illusions, useful, convenient, but ultimately incorrect? JWST had not disproven dark matter, but it had wounded the certainty surrounding it. And certainty, once wounded, bleeds into every equation, every model, every assumption. The section ends on a thought scientists avoided voicing aloud but quietly feared. Dark matter, the invisible architect of the cosmos, might not be what we've assumed for decades. And if the architect is misunderstood, then the cosmic structures it supposedly built may need an entirely new explanation. They called it the line no one wanted to cross, the boundary between reasonable speculation and the kind of ideas that made entire careers tremble. Yet as JWST's findings continued to defy every comfortable assumption, scientists found themselves drifting toward theories they had long dismissed as fringe, even absurd. The physics nobody wanted to consider had arrived at the center of the conversation, and it cast a shadow long enough to unsettle even the most grounded minds in cosmology. The data was not merely nudging them, it was forcing them to reevaluate foundations they once believed unshakable. The earliest discussions happened in hushed tones, behind closed office doors and in late-night conference messages. Researchers who had spent decades refining the standard model began to confess an unease they could barely articulate. The universe was not just surprising, it was rebellious. The anomalies weren't single cracks. They were spreading fractures, and beneath them lay something deeper, stranger, and far less friendly to traditional physics. It was becoming impossible to avoid the looming question. What if the early universe operated under physical laws fundamentally different from the ones that rule today? This idea was considered dangerous because it shattered one of cosmology's most comforting assumptions, that the laws of physics are universal and unchanging. If gravity, energy behavior, quantum interactions, or even the passage of time behaved differently in the first few 100 million years, then every equation describing cosmic evolution would need to be rebuilt. The narrative of the universe would no longer be a neat progression, but a landscape of shifting rules, transitions, and hidden phases no one had ever accounted for. Some theorists began to explore these forbidden possibilities. They wondered if exotic particles existed only in the earliest epochs, influencing formation cycles before decaying into nothingness. Others proposed that time itself may have flowed unevenly, a universe where minutes stretched or folded depending on the density of energy and curvature. A few dared to question the stability of fundamental constants. What if the speed of light had been slightly different? What if the strength of gravity varied with temperature? What if the fine structure constant was not so fine in the beginning? Such ideas gave physicists chills, not because they were fantastical, but because they were plausible enough to explain the impossible galaxies JWST revealed. Yet each theory carried its own unsettling implications. A variable speed of light would rewrite the entire cosmic timeline. Time dilation in the early universe would undermine every model of stellar evolution. Shifting constants would imply that nature itself once existed in a volatile, experimental state. The universe would no longer be a fixed stage but a dynamic, evolving framework, one that changed its own rules without warning. The emotional weight of these theories grew heavier as more data arrived. Galaxies appeared too quickly. Structures formed too efficiently. Chemical elements existed before their time. The early universe looked like a place where physics bent, twisted, or possibly broke. And this forced scientists to confront an even darker possibility. What if the anomaly didn't just point beyond physics, it pointed beyond reality as we understand it? For centuries, science had been built upon the assumption that the universe was knowable, that its rules were discoverable, measurable, and consistent. The JWST anomaly threatened that confidence. If the early cosmos behaved in ways that defied all physical models, then perhaps human understanding was brushing against a frontier where intuition, mathematics, and logic themselves began to unravel. Some physicists proposed the existence of early universe phase transitions, hidden eras where spacetime behaved like a fluid or a superheated medium, generating structures rapidly before cooling into the physics we recognize today. Others explored the possibility of primordial fields or forces that flickered in and out of existence like brief cosmic storms. These ideas painted the early cosmos not as a simple expansion, but as a chaotic arena of competing effects, a battleground of forces, each shaping the universe in ways no telescope can directly observe. Still more unsettling were the whispers about emergent physics. What if the laws of nature themselves emerged gradually, like patterns forming in a cooling crystal? That would imply that the universe had a kind of infancy where its rules were still crystallizing, an era where causality, gravity, quantum behavior, or energy flow did not yet operate in stable, predictable ways. Such a universe would not merely be unknown, it would be unknowable. The scientific community struggled with the emotional toll of these suggestions. To consider them meant accepting that the universe was not the clean, elegant system so many textbooks celebrated. It was messy, chaotic, perhaps even intentionally obscure. The shock among researchers felt almost existential. The more they opened their minds to uncomfortable theories, the more it seemed reality itself was slipping into a deeper, more mysterious form. But the most frightening idea of all was the one no one wanted to write on paper. What if the anomaly doesn't point toward new physics, but toward something outside physics altogether? Something about perception, consciousness, observation, or the nature of reality as a construct. The possibility hovered like a shadow, unspoken but present, as though the universe were hinting at layers of meaning far beyond equations. By the time JWST completed its first year of observations, the forbidden theories were no longer fringe, they were becoming necessary. The early universe was too strange to fit inside any existing framework. And so the scientific community, reluctantly at first and then with growing urgency, crossed the line they once vowed never to approach. They entered the realm of the physics nobody wanted to consider. And with each step, it became clearer that the anomaly might point not just beyond physics, but beyond the very idea of a single, stable, knowable universe. For nearly a century, the Big Bang has served as the opening chapter of the universe's story, a moment of explosive birth, expansion, and transformation. It was elegant, powerful, and comforting in its simplicity. But JWST's discovery struck that narrative like a hammer against glass. Suddenly the clean timeline of cosmic history appeared tangled, rushed, and strangely inconsistent. Galaxies too massive for their era, stars too evolved for their age, chemical elements too mature for the universe's youth, all of it hinted that the standard picture of the Big Bang might be incomplete. Scientists found themselves wondering if the event they had spent decades describing was not the universe's true beginning, but merely the beginning of a later stage. Perhaps the cosmos had a deeper, more complex origin story hidden beneath the surface, a prologue lost to time yet revealed through ancient light. The tension grew as astronomers revisited the iconic image of the universe's earliest moments, a blinding fireball expanding outward, cooling, smoothing, seeding matter across the void. But JWST's data didn't line up with that calm, gradual unfolding. Instead, it suggested a universe erupting with creativity almost immediately, assembling structured, mature systems far too early. The contrast felt jarring, like discovering advanced civilizations living in the ruins of a world that should still be forming oceans. If the Big Bang was truly a clean beginning, where did the complexity come from? Some physicists proposed the existence of pre-Big Bang conditions, perhaps a contracting universe that rebounded, or a phase transition in a deeper cosmic field. Others speculated about hidden dimensions or primordial structures that predated the explosion. Whatever the explanation, the unsettling implication was the same. The Big Bang may not have been the absolute beginning, but the visible beginning of something older and stranger. The emotional shift within the scientific community was almost cinematic. Researchers who once spoke of the Big Bang with absolute certainty began to describe it with careful hesitation. They questioned whether inflation, the rapid expansion thought to have smoothed the early cosmos, truly behaved as predicted. Some wondered if inflation hid more than it revealed, if it buried a previous era beneath a blanket of stretched-out spacetime. Imagery of the early universe transformed from a single blazing moment to a layered, evolving sequence of events, each phase leaving faint fingerprints on the cosmic background. JWST's revelations pushed scientists to imagine the universe not as a story with one beginning, but as a narrative with chapters erased, rewritten, or distorted by forces we barely understand. And each new observation felt like a recovered page from that lost history. At the heart of the debate lay a single question. Did the Big Bang happen the way we think it did? The idea was both thrilling and terrifying. If the early galaxies were truly as massive and complex as they appeared, then the universe must have evolved at a pace far beyond current models. That suggested something extraordinary occurred before or during the Big Bang, something that primed the cosmos for accelerated formation. Perhaps energy fields behaved differently. Perhaps quantum fluctuations were far more intense. Perhaps gravity had a strength or fluidity in those first moments that allowed structures to form rapidly. These ideas painted the early universe not as a tranquil birth, but as a roaring inferno of competing forces, each shaping the cosmos with aggressive efficiency. The origin story became less like a gentle dawn and more like a storm, violent, unpredictable, and filled with hidden processes unfolding faster than our theories allow. Ancient cultures often described creation as a sequence of cosmic cycles: expansion, destruction, rebirth. Amazingly, some scientists began drawing parallels. Modern physics had rejected cyclical cosmologies for decades, but JWST's observations reopened the discussion. Could the universe have experienced previous epochs? Could remnants of an earlier reality have survived the transition into ours? Some models suggested that information might leak across cosmic boundaries, leaving subtle imprints detectable only in the earliest galaxies or in the cosmic microwave background. These possibilities felt mythic, yet grounded in mathematical rigor. The line between scientific explanation and ancient intuition blurred. The universe no longer resembled a simple explosion but a grand, layered unfolding, perhaps even a universe emerging from the ashes of another. As researchers grappled with these possibilities, the philosophical implications deepened. If the Big Bang was not the beginning, then human understanding of the cosmos had been rooted in a partial truth. The universe might be older, larger, or more intricate than anyone imagined. It might contain structures or information predating the observable horizon. The thought was both humbling and exhilarating. JWST's anomalies became more than scientific puzzles. They became existential questions about origins, causality, and the nature of time. The bright, confident narrative of the Big Bang dimmed into something more mysterious, more cinematic, and far more profound. The universe, it seemed, was not a story that began with a single moment of creation, but a saga whose opening chapters remain hidden behind a veil of ancient light. The idea that our universe might be only one branch among countless others has always lingered at the edges of scientific imagination, a quiet speculation that hovered where physics, philosophy, and wonder intersect. But when the JWST began returning images that seemed to warp the boundaries of what a young cosmos should look like, the multiverse hypothesis, once dismissed by many as an indulgent thought experiment, slipped back into the conversation with a newfound and unsettling relevance. Researchers who once avoided the term altogether now found themselves sketching diagrams of branching timelines, inflationary bubbles, and overlapping cosmic histories on white boards that previously held only equations rooted in classical certainty. The idea that our universe might be only one branch among countless others has always lingered at the edges of scientific imagination, a quiet speculation that hovered where physics, philosophy, and wonder intersect. But when the JWST began returning images that seemed to warp the boundaries of what a young cosmos should look like, the multiverse hypothesis, once dismissed by many as an indulgent thought experiment, slipped back into the conversation with a newfound and unsettling relevance. Researchers who once avoided the term altogether now found themselves sketching diagrams of branching timelines, inflationary bubbles, and overlapping cosmic histories on white boards that previously held only equations rooted in classical certainty. The images themselves were innocent enough, tiny flecks of light, distant and faint. But their arrangement, their brightness, and above all their age made them anomalies that refused easy explanation. The galaxies appeared too massive, too structured, too early in cosmic history. Instead of resembling tentative cosmic seedlings, they looked like mature giants that had no right to exist so soon after the Big Bang. It was as though the universe, instead of beginning as a singular and orderly expansion, bore the fingerprints of a more complicated birth. Perhaps not a single beginning at all, but a tapestry woven from multiple threads of origin. This growing suspicion led scientists to revisit theories they had long tucked away. One of the most compelling was the idea that inflation, the rapid, hyper-accelerated expansion thought to have occurred in the first sliver of a second, might not have been a uniform event. Instead, it could have spawned pockets of reality that developed differently, each with its own physical constants, laws, and timelines. In this view, the cosmos becomes an expansive foam of universes, each budding off from the primordial fabric like bubbles rising through boiling water. Some would collapse almost immediately. Others would stretch, cool, and evolve into something rich and structured. And perhaps, just perhaps, some of the oldest galaxies JWST captured were not truly part of our universe in the way we traditionally understand the term, but remnants of a nearby cosmic branch, glimmers from a sibling universe intersecting with our sight line. This possibility unsettled even seasoned cosmologists. The multiverse had always been an abstract idea, mathematically permissible but nearly impossible to test. Yet the anomaly in the early universe data whispered a dangerous suggestion. What if the boundaries between universes were not sealed as tightly as once believed? What if, under extreme conditions at the dawn of everything, the edges of two cosmic domains brushed against one another, leaving behind structural echoes that astronomers are only now beginning to detect? A fleeting overlap, lasting no more than fractions of a second, could imprint patterns in matter distribution, influence star formation, or shift the expected timelines of galactic development. That kind of subtle nudge might be enough to produce the galaxy's now troubling standard cosmology. Some theorists proposed that these overlapping domains might be akin to interference patterns on the surface of a pond. When two waves meet, they create regions of constructive and destructive interference, peaks and troughs that appear structured and intentional even though they arise from simple interactions. In the same way, two adjacent universes could momentarily intersect during inflation, creating zones where matter clumped more efficiently or where gravitational behavior differed ever so slightly from the predictions of a solo universe. These regions, frozen into the cosmic landscape and carried forward by expansion, might now appear in JWST's deep field images as anomalies that defy the expected rhythm of early cosmic assembly. Others took a bolder stance. They suggested that what researchers call our universe is not a self-contained bubble but part of a larger hierarchical structure, a multiversal web where energy and information leak between domains in ways we do not yet understand. In this framework, universes could be born not from isolated explosions but from branching processes, each new universe budding from a parent or sibling. The earliest galaxies, then, might belong to an ancestral lineage far older than our own cosmic clock. The light we capture would be ancient not just in distance but in pedigree, belonging to a history predating the beginning we thought we understood. Still, skeptics countered that invoking a multiverse risked explaining too much too easily. If anomalous galaxies could be attributed to another universe, then nearly any contradiction in data could be swept into the convenient category of interuniversal interference. Yet the proponents responded that this very concern underscored how deeply the anomalies challenged established models. If standard cosmology could not account for the data without contorting itself into unstable shapes, then perhaps the simplest explanation, however extraordinary, was that the universe's beginning was never singular. Complexity might not be a flaw in the model but a feature of reality. As the debate intensified, imagination and analysis intertwined. Visual metaphors became common. Some compared the multiverse to a vast orchard where each universe is a fruit growing from the same tree, sharing nutrients from a deeper substrate. Others imagined a cosmic loom weaving multiple threads together, each universe a strand that occasionally intertwines with its neighbors before diverging again. And some envisioned branching tunnels carved into eternally inflating space, each tunnel a timeline unfurling with its own destiny, some brushing shoulders like commuters in a crowded station before disappearing into their respective futures. These metaphors helped scientists communicate the scale of the idea, but they did little to settle the underlying question. Could evidence of another universe truly be hidden within the light from galaxies billions of years old? And if so, how could we ever distinguish that evidence from the noise of instrumentation, from the uncertainties of models, or from our own cognitive longing for grand narratives? Yet the more data poured in, the more the conversation shifted from, "Is this possible?" to, "How could this be tested?" Some proposed analyzing the distribution of galaxy shapes, looking for patterns inconsistent with gravitational evolution in a single, isolated universe. Others suggested scanning the cosmic microwave background for subtle geometries, ripples, edges, or cold spots, that could betray the signature of a past collision or overlap between universes. A few theorists even speculated that dark energy or dark matter might be the shadow of neighboring universes, their gravitational fingerprints reaching across the boundary like a hand pressed lightly against a window. Even with these ideas swirling, the emotional core of the debate was perhaps the most striking. For many researchers, the multiverse concept felt like stepping into an existential wilderness. If the cosmos truly holds countless variations of reality, then our universe, with all its galaxies, stars, and fragile strands of life, might be just one story among infinitely many, no more central or definitive than a single grain of sand on a cosmic shore. The early galaxies revealed by JWST, rather than offering new clarity, had opened a door to bewilderment that was both exhilarating and disorienting. And yet, amid this philosophical vertigo, a sense of awe prevailed. For all the fear and uncertainty, there was something profoundly beautiful in the notion that the universe might not be alone. That creation might be a repeating process, echoing across unimaginable scales. That beginnings might be multiple, not singular. That existence itself could be richer, stranger, and more layered than any single narrative could contain. In the end, the question that emerged from the data was not simply whether the early galaxies were too massive or too old. It was deeper, more poetic. What if the story we have been telling about the universe's origin is only one chapter in a much larger book? One that spans not just time and space, but entire realities stacked, branching, or drifting alongside our own. And what if, through some cosmic coincidence or hidden connection, JWST has given us a fleeting glimpse into one of those neighboring stories? The possibility hangs in the air like a fragile thread of light, linking our world to countless others we may never fully see but can now imagine with a clarity that borders on revelation. The possibility hangs in the air like a fragile thread of light, linking our world to countless others we may never fully see but can now imagine with a clarity that borders on revelation. When the first JWST images revealed galaxies that seemed to violate every expectation, many physicists quietly acknowledged a possibility they had once dismissed as too extravagant to consider. If the early universe looked wrong according to our single-universe model, then perhaps the model itself was too narrow. Maybe the cosmos was not a lone, continuous story but one chapter among countless volumes, each with its own beginning, its own physical rules, and its own timeline of cosmic evolution. This idea did not require abandoning science, it required expanding it. The anomalies were no longer viewed as mistakes but as potential fingerprints from a universe adjacent to ours. This shift opened an intellectual horizon far larger than the one cosmology had previously explored, encouraging scientists to ask whether JWST might be catching glimpses of boundaries where universes brush against each other. Some researchers proposed that our universe could be part of an enormous cosmic landscape, a vast multidimensional terrain where different regions possess different fundamental constants. In this picture, our universe formed like a bubble in a foam of countless others, each bubble expanding according to its own laws. If two such bubbles ever collided or interacted, their meeting might leave scars, subtle distortions in temperature, structure, or the distribution of matter. The strange appearance of early, overdeveloped galaxies suddenly seemed less surprising. Perhaps these structures were shaped not only by our universe's evolution but by the gravitational influence or energetic imprint of another universe nearby. Such an idea felt bold, yet it provided an elegant way to explain why the early cosmos appeared too mature, too structured, and too fast-moving to fit inside the standard framework. Another school of thought focused on the idea of branching universes, where every quantum event could generate alternate outcomes. According to this view, rather than a single Big Bang giving rise to a single timeline, reality might perpetually divide into countless parallel histories. If so, the early cosmos might bear subtle echoes of these branching processes. Some physicists speculated that during the universe's formative moments, when quantum fluctuations dominated, these branches interacted more strongly, producing regions where matter gathered unusually quickly or where the rules governing structure formation briefly overlapped. JWST's anomalous galaxies could then be seen as artifacts of that ancient entanglement, regions where the boundaries between multiple histories briefly blurred before stabilizing into the universe we inhabit today. The galaxies would not represent errors in physics but traces of a more complex beginning. Other theorists revisited the concept of cosmic cycles, universes that die and rebirth, each new beginning seeded with the remnants of the previous one. Under this framework, the early galaxies detected by JWST could be embers from an older universe, carried through the transition like sparks preserved through a cosmic collapse. These embers might have provided ready-made structures around which new matter could coalesce, accelerating galaxy formation far beyond what the standard Big Bang timeline allows. While speculative, the idea resonated with the surprising order and scale observed in the earliest cosmic images. The anomalies no longer seemed like premature masterpieces but rather inheritances, hints that our universe might be part of an ancient lineage stretching backward through cycles of expansion and renewal. Philosophers entered the conversation with perspectives that broadened the discussion even further. They pointed out that if multiple universes exist, then our observations, no matter how puzzling, represent only one perspective among infinite possibilities. The universe might appear finely tuned for life, structure, or rapid formation not because it was designed that way, but because countless universes with different properties exist, and we naturally find ourselves in one where conditions permit observers to emerge. The early galaxies detected by JWST, then, could simply reflect the parameters of our particular universe, parameters that allow complexity to arise faster than older models predicted. Instead of breaking the rules, the universe might merely be revealing the specific combination of constants that shaped its destiny. Still others imagine more audacious possibilities. What if universes occasionally exchange information? What if quantum entanglement, instead of being confined to our local spacetime, connects distant realities? Under such hypotheses, the early cosmos might have been a conduit, a place where signals, fluctuations, or patterns from other universes briefly passed through. These transmissions could leave faint but measurable features, strange alignments, unexpected densities, or galaxies that appear too evolved to be products of our universe alone. JWST's findings might not be evidence of alternative universes themselves but evidence of interactions that occurred when everything was new and boundaries were not yet firm. As these ideas circulated, the emotional landscape of cosmology transformed. Scientists accustomed to thinking in terms of one universe now grappled with the possibility of many, each with its own story and structure. Instead of diminishing the significance of our cosmic home, this vision made it far more profound. Our universe became one voice in a chorus, one pattern in a tapestry of incomprehensible scale. The early galaxies, shining fiercely from across 13 billion years, felt like messages not just from our past but from the broader architecture of existence. They suggested that creation might not be a single event but a sprawling network of beginnings, each influencing the others in ways we are only starting to imagine. The most unsettling implication was also the most inspiring. If multiple universes exist, then our understanding of reality is still in its infancy. JWST may have given us not only a glimpse of ancient galaxies but a glimpse of something larger, a cosmic backdrop where many worlds arise, evolve, intersect, and fade. The anomalies that puzzled astronomers could be clues pointing toward this larger framework, encouraging humanity to rethink what a beginning truly means. In this emerging vision, the universe is not a solitary story but part of a vast library of existence, each universe a volume filled with wonders we are only beginning to comprehend. Humanity stands on the edge of a scientific threshold, trying to weave the scattered clues of the cosmos into a new coherent story. As researchers gather the data from JWST and compare it with decades of theoretical predictions, a shape begins to form, something subtle, intricate, and far more dynamic than the universe once imagined. The tension between old models and new evidence becomes a creative pressure, pushing scientists toward ideas they once avoided. Each anomalous galaxy that appears too bright or too mature now becomes a brushstroke in a grander narrative, suggesting that the architecture of the cosmos may have been front-loaded with possibilities. Instead of a universe that grows slowly into complexity, it may be one that bursts with creative potential from the very start. This emerging picture forces cosmologists to reconsider foundational assumptions. Perhaps the early universe wasn't governed by a single smooth progression of events but by a series of overlapping processes. Slight asymmetries in matter, tiny fluctuations in the quantum fabric, or subtle interactions between forces might have accelerated cosmic development in ways standard equations struggle to describe. As the pieces come together, the feeling in the scientific community shifts. Rather than perceiving the JWST findings as contradictions, researchers begin to see them as clues pointing toward a more flexible and layered understanding of creation. The universe starts to look less like a machine and more like a living system, dynamic, adaptive, and capable of rapid self-organization. Yet this new story is anything but simple. For every explanation that seems promising, contradictory evidence emerges. Some galaxies appear to have formed too quickly, but others match predictions perfectly. Some regions of space seem dense with unexpected structures, while others remain nearly empty. These inconsistencies do not weaken the developing narrative, they enrich it, suggesting that the early cosmos may have been far more varied from place to place than previously assumed. Instead of a uniform expansion, perhaps the universe experienced pockets of accelerated formation, regions where matter clumped together with unusual efficiency. This patchwork development hints at a cosmos that allowed complexity to bloom differently across its vastness. As theories evolve, scientists begin integrating models from fields that rarely intersected before. Ideas from quantum gravity, string theory, plasma physics, and early universe thermodynamics begin to merge. The emerging synthesis describes a universe shaped not by one dominant principle but by the interplay of many forces, each contributing to a tapestry of rapid transformation. This interdisciplinary approach feels both revolutionary and necessary. The anomaly revealed by JWST becomes a catalyst for unity across scientific disciplines, encouraging collaboration and challenging long-held assumptions about how cosmic structure emerges. With each new piece of evidence, the tone of scientific discussion transforms from alarm to cautious excitement. The possibility that the universe was more efficient at forming structure than expected no longer feels like a contradiction. It becomes a guiding principle. Perhaps galaxies formed early because conditions were uniquely fertile. Perhaps star-forming material condensed with extraordinary speed due to processes not yet fully understood. Or perhaps the cosmic timeline itself bends in ways that defy linear intuition. The new cosmic story taking shape is one where the universe is not merely following a script but inventing it moment by moment. This shift in perspective inspires a deeper philosophical reflection. If the universe began with such rapid creativity, what does that imply about its nature? Is complexity an accident or an inherent tendency? Does the universe strive toward structure, or did the earliest moments simply allow anything that could form to form immediately? These questions add emotional weight to the scientific narrative, reminding us that cosmology is not only about data and equations but about humanity's attempt to understand its place in a vast, evolving reality. As the narrative sharpens, researchers recognize that they are uncovering more than a scientific mystery, they are witnessing a paradigm in transition. Old models are not discarded, they are expanded. New theories do not replace the old, they extend them into realms once thought unreachable. The universe becomes more fascinating precisely because it refuses to fit neatly into any single framework. JWST, meanwhile, continues to reveal structures that push the limits of imagination, providing both the puzzle and the momentum needed to solve it. By the end of this emerging story, one conclusion stands out: the universe is richer, faster, and more expressive than ever believed. The early cosmos was not a blank canvas but a stage already filled with actors, each moving with surprising purpose. The story taking shape is one of transformation and possibility, where anomalies are not threats but invitations. And as scientists continue to refine this evolving picture, humanity is left with a sense of awe, a recognition that the cosmos is not only stranger than expected but more elegantly interconnected than any previous generation dared to imagine. As humanity pushes further into the cosmos with each new generation of telescopes, the realization grows that JWST is only the beginning of a much larger scientific awakening. The universe has revealed just enough mystery to provoke a new era of exploration, one built not on guesswork but on machines capable of probing deeper, sharper, and faster than anything that has come before. The scientific community stands at the threshold of a technological renaissance, preparing instruments that will challenge not only the anomalies uncovered by JWST but the very foundation of cosmology itself. These future machines promise to see farther back in time, peel away cosmic veils once thought impenetrable, and expose processes still hidden behind the fog of the early universe. If JWST triggered the questions, these new observatories may finally attempt the answers. At the forefront of this next wave is the extremely large telescope, a towering ground-based giant whose mirror segments form a massive eye on the universe. It is designed to capture faint signals from the earliest galaxies with unprecedented clarity, pushing past the limits of current observations. Scientists believe this machine will scrutinize the structures JWST uncovered, those oversized, overgrown galaxies that should not exist, and reveal whether they are truly ancient or shaped by some trick of cosmic evolution. The idea that a telescope could slice through billions of years of distance and expose the true nature of these objects fills astronomers with both excitement and anxiety. If the ELT confirms what JWST suggests, the universe may be even more radical than previously imagined. Orbiting above Earth's atmosphere, another future mission prepares to take shape, the Nancy Grace Roman Space Telescope. With its immense field of view, Roman will map the cosmos not as a scattered collection of snapshots but as a vast, interconnected tapestry. It will search for patterns in galaxy formation, gravitational lensing, and the distribution of dark matter across cosmic history. By comparing these patterns with JWST's detailed images, scientists hope to determine whether the early universe was truly forming structure at impossible speeds or whether unseen forces were nudging matter into place. The Roman telescope surveys will offer a sweeping view, revealing context that JWST alone cannot capture. In this way, it will act as the cosmic cartographer to JWST's cosmic microscope. Further into the future, plans for the next great leap, LUVOIR, begin to stir the imagination. This proposed mega-observatory, with a mirror far larger than JWST's, could reveal not only early galaxies but the atmospheres of distant worlds, the fingerprints of chemical processes, and perhaps even the early signs of life. LUVOIR represents humanity's boldest ambition, to build an instrument capable of rewriting not just cosmology but our understanding of existence itself. If approved and launched, it could observe the faintest echoes of the universe's first moments, capturing details far beyond what JWST's current capabilities allow. For cosmologists, LUVOIR is nothing less than a machine built to chase the universe's origin story to its most elusive chapters. Meanwhile, breakthroughs in computational astronomy promise to complement these physical machines. Quantum-based simulators, next-generation supercomputers, and AI-driven models will test each new observation against millions of theoretical universes. These tools will allow scientists to explore scenarios where dark matter behaves differently, where gravity shifts its strength, or where the early universe evolved according to rules that no human theory has yet described. As these simulations grow more sophisticated, they will not merely follow observations. They will predict new ones, guiding telescope time like a compass cutting through cosmic uncertainty. In their own way, these machines are telescopes turned inward, gazing into the mathematical soul of the cosmos. Yet even with all this power, an unanswered question looms. What if the next machines deepen the mystery instead of solving it? What if the early universe grows stranger the closer we look? This possibility haunts and motivates scientists in equal measure. Every new observatory offers clarity but also exposes complexity. Every improved simulation unlocks insight but also reveals hidden assumptions. In this sense, the future machines represent not just tools but philosophical tests. They will determine whether the universe ultimately obeys a comprehensible order or whether its earliest moments exist beyond the reach of human intuition. Still, the emotional force driving these missions is clear: humanity's relentless desire to know. The construction of each telescope is an act of collective faith, a statement that answers matter, even when they challenge everything we believe about space, time, and reality. As the blueprints sharpen and the components assemble, scientists feel the weight of history settling on their shoulders. Future generations will look back on these machines as monuments to curiosity, vast, delicate instruments built to chase the truth across the darkness. In the end, the future machines that will answer everything represent more than hardware and engineering. They symbolize the next chapter in humankind's relationship with the cosmos. JWST has opened the door to new mysteries, but the instruments that follow will walk through it, carrying with them the hopes, fears, and endless questions of a species determined to understand its origin. Whether they bring confirmation or contradiction, revelation or bewilderment, their mission remains the same: to illuminate the shadows of the universe's beginning and bring humanity one step closer to grasping the full story of creation. As the scientific community absorbs the implications of JWST's discoveries and anticipates the capabilities of upcoming observatories, a deeper question begins to emerge, one that extends beyond data, models, and theoretical frameworks. It concerns the emotional and existential weight of confronting a universe that refuses to fit neatly into human expectations. The early cosmos revealed by JWST is not merely a scientific anomaly, it is a philosophical provocation, challenging humanity to rethink its place in the vast, unfolding story of existence. Every surprising galaxy, every unexpected chemical signature, and every distortion in spacetime hints at a cosmos far more layered, dynamic, and untamed than previous generations believed. In this sense, the scientific journey is becoming something more profound, a confrontation with the limits of human understanding. This confrontation does not discourage scientists. Rather, it fuels them. Researchers across disciplines, cosmology, astrophysics, quantum theory, computational mathematics, are increasingly united by a shared sense of urgency. The universe is offering hints, clues, and contradictions at a pace unmatched in modern scientific history. These insights demand new thinking, new methods, and new collaborations. For the first time, entire scientific communities are revisiting assumptions once considered untouchable, such as the uniformity of the early universe or the predictability of gravitational behavior under extreme conditions. The willingness to question the foundations rather than merely refine them marks a critical shift in mindset. It represents a scientific culture no longer afraid to confront the possibility that long-standing models may require radical revision. Beyond laboratories and observatories, this scientific transformation is inspiring a broader cultural shift. As discoveries gain public attention, people around the world begin reshaping their own understanding of the cosmos and humanity's role within it. The awe triggered by JWST's images is no longer confined to academia. It resonates across social platforms, classrooms, and conversations. For many, these revelations are not just scientific facts, they are emotional experiences. They spark wonder, humility, and a renewed sense of connection to something vast and ancient. They remind society that despite all technological progress, humanity remains a species of explorers, driven by the same curiosity that led our ancestors to map stars with naked eyes. This shared awe also serves as a bridge between cultures. Different civilizations throughout history developed their own cosmologies, myths, and sky traditions. Today, modern astronomy unifies them under a common, evidence-driven vision of the universe's origins, yet it preserves the emotional resonance those ancient stories carried. When people see JWST's first galaxies or the structure of a distant nebula, they tap into a universal heritage of stargazing and meaning-making. In that sense, every new discovery carries both a scientific truth and a human truth. The cosmos belongs to all of us. Despite this unity, the emotional weight of confronting cosmic mystery brings its own challenges. Some individuals feel overwhelmed by the vastness and strangeness of the universe, experiencing what psychologists call the cosmic perspective shock. This phenomenon, similar to the overview effect described by astronauts, can cause a mix of awe, insignificance, exhilaration, and existential questioning. Yet for many, this emotional turbulence becomes transformative. It inspires creativity, philosophical reflection, and a re-evaluation of personal priorities. By revealing how small we are, the cosmos paradoxically deepens our appreciation for life, relationships, and the fleeting moments that shape our human experience. In academia, recognizing the emotional and philosophical dimensions of cosmic discovery is becoming increasingly important. Scientists are now acknowledging that data alone does not define progress. The stories they tell about that data also matter. Communicating the mystery, beauty, and uncertainty of the universe is essential, not only to inspire future generations of researchers but to foster a society capable of engaging thoughtfully with scientific truth. As new telescopes and missions prepare to expand our cosmic vision, the role of narrative, outreach, and public curiosity becomes even more crucial. The universe is speaking in signals of light, gravity, and time, but it is up to humanity to translate those signals into meaning. Ultimately, the emotional connection to the cosmos, this mixture of wonder, fear, curiosity, and humility, acts as the invisible engine behind scientific advancement. Every groundbreaking discovery begins as a simple human question: what is out there? The pursuit of that question has led to the construction of telescopes, the development of theories, and the relentless search for patterns in the darkness. As we stand on the brink of even greater revelations, it becomes clear that the universe is not only a frontier of physics but a mirror reflecting humanity's deepest aspirations. And in that reflection lies the true power of exploration, the chance to understand not just the cosmos but ourselves. As scientists and philosophers confront the full weight of the JWST anomaly, a deeper realization begins to crystallize, one that transcends any single model, theory, or cosmic narrative. The universe that once seemed predictable in its expansion, governed by clean equations and elegant symmetries, has revealed an unpredictability that shakes even the most fundamental assumptions. The early galaxies are not merely outliers or curiosities, they are signals from a universe that behaves with a kind of creative intensity we never anticipated. It is as if the cosmos is whispering that its story is far more intricate, far more layered, and far stranger than imagination alone could ever conceive. And yet, paradoxically, this strangeness does not push us away, it pulls us in. For every answer uncovered, a dozen new questions emerge, each one hinting at a universe that invites wonder rather than surrender. As researchers dig deeper into the data, they begin to recognize that the anomaly is not isolated. Subtle inconsistencies in cosmic microwave background measurements, unexplained variations in gravitational lensing maps, and unexpected distributions of dark matter all seem to echo the same message. The universe may be operating under principles we have not yet discovered. This realization forces scientists to rethink long-standing assumptions about structure formation, particle behavior, and the relationship between spacetime and energy. In doing so, they find themselves confronting not only scientific mysteries but emotional ones as well. To reach for an answer that may overturn decades of work requires courage, humility, and a willingness to embrace uncertainty at a scale rarely demanded in any field. Yet the more uncertain the cosmos becomes, the more alive it feels. The early universe, once imagined as a chaotic but uniform expanse, is beginning to resemble a place of surprising creativity, where galaxies ignite earlier than physics should allow and structures rise with astonishing speed. This vitality suggests a universe that is not simply expanding but unfolding, blooming, evolving in ways that stretch the boundaries of imagination. In this view, the cosmos becomes less like a machine and more like an organism, dynamic, unpredictable, and filled with emergent behaviors that cannot be reduced to equations alone. As this perspective grows, researchers begin to appreciate the emotional landscape that accompanies scientific discovery. The strangeness of the universe is not merely an intellectual puzzle. It is an experience that shapes the psyche. Scientists describe moments of awe when they realize the scale of what they are observing, moments of fear when familiar models collapse, and moments of exhilaration when a new possibility takes shape. These experiences reveal that the human mind is not separate from the cosmos it studies. Instead, every observation becomes a conversation, a call and response between human curiosity and cosmic complexity. This conversation becomes even more profound when researchers confront the possibility that some aspects of the universe may remain permanently beyond human understanding. While science has always sought answers, the universe revealed by the JWST anomaly seems to gesture toward an infinite depth of mystery. Far from discouraging exploration, this infinite horizon invites it. For many scientists, the realization that the cosmos may never be fully solved becomes a source of comfort rather than frustration. It transforms the universe from a problem to be conquered into a companion on an endless journey of discovery. Outside the scientific community, this sense of cosmic strangeness resonates with the public. People around the world experience a renewed sense of wonder when they see the earliest galaxies, the warped arcs of gravitational lenses, or the delicate spirals of ancient cosmic structures. These images stir emotions that transcend cultural boundaries. They remind humanity that, despite all differences, we share a common origin written in starlight and cosmic dust. The strangeness of the universe becomes a unifying story, one that dissolves borders and invites reflection on the vastness of existence. As this story spreads, it influences art, literature, music, and philosophy. Creators draw inspiration from the universe's unpredictability, crafting works that mirror the strange beauty of cosmic formation. Philosophers revisit age-old questions about time, causality, and the limits of knowledge. In classrooms, students look at JWST images and feel their minds stretch to accommodate possibilities they never considered. The universe becomes not just an object of observation but a catalyst for imagination, shaping human thought in ways that ripple across generations. Amid this cultural and scientific transformation, one idea becomes increasingly clear: the universe's strangeness is not a flaw but a feature. Its unpredictability is what makes exploration meaningful. If the cosmos followed a perfectly predictable pattern, curiosity would wither. Instead, the universe offers endless surprises, each one encouraging humanity to push further into the unknown. This unpredictability becomes a testament to the richness of existence, a reminder that there are more things in the universe than any single mind or even species could ever fully grasp. As researchers continue their work, they begin to see beauty in the very act of not knowing. The unanswered questions become stars in the intellectual sky, points of light guiding future generations. They reveal that the universe is not static but alive with possibility. And in this realization, humanity finds a new kind of connection to the cosmos, one that blends science with emotion, logic with wonder, and knowledge with the infinite space of the unknown. Ultimately, this is the lesson the universe seems to be offering. Not that it is chaotic or incomprehensible, but that it is endlessly surprising. Its strangeness is an invitation to explore without expectation, to imagine without limitation, and to embrace the mystery that makes existence so profoundly compelling. In the vast darkness between galaxies, in the ancient light from the universe's first moments, and in the silent drift of cosmic structures, there is a message waiting for all who seek it. The universe is stranger than imagination, and that strangeness is the very fabric of its beauty. In its vastness we find humility, in its mysteries we discover purpose, and in its silent depths we sense a calling that transcends boundaries and invites endless curiosity. Eternally. As scattered theories begin to converge into a coherent narrative, scientists realize that the cosmos is presenting not a contradiction, but a new story, one that reshapes our understanding of what the universe is and how it came to be. Across observatories, research centers, and bustling conference halls, a subtle shift occurs. Rather than resisting the anomaly, researchers start to weave it into a broader tapestry, one that portrays the early universe not as a quiet, slowly assembling structure, but as a fierce engine of creation. Galaxies forming too early, stars igniting too fast, matter clustering with impossible efficiency. These become chapters in a cosmic biography that is more dynamic than the models of the past ever allowed. The universe is no longer a passive stage but an active participant in its own evolution. This emerging story reveals a cosmos that front-loads complexity, as though the earliest epochs were infused with a kind of cosmic ambition. Instead of gradual growth, the universe appears to leap forward, constructing vast star systems and massive galaxies with a speed that borders on miraculous. For decades, scientists assumed that simplicity governed the beginning and complexity emerged later. But the JWST anomaly flips this expectation on its head. It paints a picture of a universe that was restless from its first moments, racing to build structure faster than the rules seemed to permit. Some researchers describe this shift as a philosophical upheaval, a transformation in how humanity interprets cosmic intention or the lack of it. As scientists piece together this new cosmic story, they recognize the importance of blending observation with imagination. The anomaly forces them to look beyond traditional boundaries, to combine physics with philosophy, and to question assumptions that once felt immovable. They explore new frameworks where gravity behaves differently in the early universe, where dark matter interacts in ways never before predicted, or where the geometry of spacetime itself may have shifted during the universe's infancy. These models do not reject established science. They extend it, stretching the conceptual fabric to accommodate discoveries that refuse to fit inside older patterns. Through simulations, researchers attempt to reconstruct the early cosmos under this new paradigm. What they see is astonishing: galaxies forming in turbulent bursts, matter flowing along cosmic filaments that thicken far earlier than expected, and the first stars seeding the universe with heavy elements at a pace that challenges nucleosynthesis models. These digital universes behave with the same audacious complexity that JWST has observed. For many scientists, this is a moment of vindication, proof that the cosmos is offering clues, not contradictions, and that those clues point toward a story that is still unfolding. Yet even as progress is made, the mystery deepens. Every new simulation opens fresh questions. Why did the universe accelerate its formation processes so dramatically? What internal mechanism pushed it toward rapid organization? And why does this early burst of activity appear so finely tuned, as though the cosmos itself were eager to bring forth structure as quickly as possible? This uncanny efficiency forces scientists to confront ideas they once dismissed as speculative. Some propose exotic physics operating only during the universe's first billion years. Others suggest that the universe may pass through cycles of intense creativity followed by quieter periods. Each hypothesis brings the narrative into sharper focus, yet each also reveals how much remains hidden. Beyond the technical details, the emotional impact of this emerging story is profound. Scientists describe feeling as though they are watching the universe reveal its autobiography, one written across billions of years and illuminated only now by the reach of modern technology. The JWST anomaly becomes a turning point, the chapter in which humanity discovers that the cosmos is not a simple expanding bubble of matter, but a dynamic, evolving entity with rhythms and behaviors as intricate as any biological system. This realization inspires awe, a sense of witnessing something ancient and alive. The public, too, is swept into the unfolding story. Images of ancient galaxies, compact, brilliant, impossibly structured, capture the imagination of people around the world. Documentaries, articles, and classroom lessons highlight the idea that the universe may be far more active and intentional seeming than once believed. In art studios, musicians' lofts, and late-night conversations, the idea spreads. The cosmos is not a static relic but a vibrant force of creation. Humanity begins to see itself as part of a narrative that stretches back to the universe's earliest heartbeat. As the evidence accumulates, a consensus slowly forms. The anomaly is real, persistent, and transformative. It signals not a failure of cosmology but an evolution of it. The new cosmic story taking shape suggests that our universe emerged with a drive toward rapid organization, that its earliest moments were marked by unexpected intensity, and that the laws governing those moments may hold secrets that will reshape physics for decades to come. The narrative is neither complete nor fully understood, but it is compelling, so compelling that even skeptics feel its gravitational pull. In quiet moments, researchers reflect on the significance of this shift. If the universe builds complexity faster than expected, what does that say about the nature of existence? Does the cosmos favor creation over emptiness? Does it seek structure, or do we impose that interpretation on it? Such questions bridge the gap between science and philosophy, revealing the deeper implications of the JWST anomaly. The universe's story is no longer just about matter and energy. It is about meaning, pattern, emergence, and the mysterious forces that sculpt reality. The momentum of discovery builds as each new paper, observation, and debate strengthens the emerging picture of a universe bursting with formative energy. Researchers who once hesitated now feel compelled to explore unconventional explanations, recognizing that the cosmos has always been more inventive than their theories. With every recalibrated model and refined dataset, the early universe becomes less of an enigma and more of a revelation, one that highlights how much of cosmic history remains untouched, waiting for the next generation of instruments to bring it into view. And so it continues. Something small. Something that shouldn't have happened. And now humanity faced anomalies on a scale larger than whole galaxies. It wasn't a problem. It was an invitation. The universe was pushing them toward a deeper truth. Suddenly, the hall lights dimmed as the next simulation loaded, this time incorporating new gravity data. The projection blossomed outward like a flower of light, revealing how the ghost web wrapped around the visible universe. It pulsed faintly as if alive. The scientists leaned forward simultaneously, breath catching in their throats. The new physics wasn't speculation anymore. It was here. It was visible. The equations running in the corner of the screen flickered through solutions no one had ever seen. Some variables drifted into imaginary numbers. Others spiked into infinities before collapsing into stable values that made no sense. Constants that should never change began fluctuating. The simulation wasn't malfunctioning. It was revealing the truth. The universe was operating under laws far more dynamic than anyone had predicted. One physicist ran a model assuming that dark matter wasn't matter at all, but geometry, folds and spacetime thickening and thinning like cloth under tension. The result was stunning. It replicated the ghost patterns almost perfectly. Another expert pushed further, proposing that dark energy might not be a force but a phase transition, an ongoing transformation sweeping through the universe like a slow, cosmic tide. Others ran simulations treating the anomalies as coherent fields, something akin to magnetic lines but woven through spacetime itself. Ideas clashed like lightning strikes. Voices rose. Equations filled whiteboards and digital walls so rapidly that assistants struggled to archive it all. Theories that once seemed radical now felt insufficient. The scientists were no longer patching holes in old physics. They were building the scaffolding of a new one. A physics that didn't just explain galaxies, it explained the ghosts inside them. Yet amid the exhilaration, fear crept in. If the universe operated under hidden rules, what else lay beneath the surface? What forces shaped spacetime before the first atoms formed? What creatures, or structures, might have emerged in epochs with laws nothing like today's? And had the impossible objects been waiting for humanity to evolve enough to finally see them? Or were they warnings? Markers left behind by something that understood the universe far more deeply than humans ever would? As the hours stretched into the night, the debate softened. The urgency faded into quiet contemplation. Screens dimmed. Equations slowed. The scientists stared at the swirling ghost cosmos suspended above them, each lost in thought. A new physics was emerging. Not a single theory. Not a neat equation. But a sprawling new frontier, chaotic, beautiful, frightening. It challenged everything humanity believed about existence. It demanded new mathematics, new tools, new ways of thinking. It shattered the illusion of a simple, elegant universe and replaced it with something raw and alive. One by one, the scientists realized the same truth. The cosmos was opening its doors. And for the first time, humanity was standing at the threshold, peering into the machinery behind reality. The final projection slowly dissolved into darkness, leaving only one lingering question echoing through the hall like a heartbeat. If this is the beginning of a new physics, what else is waiting to be discovered in the shadows of the universe? You said. Amid this intellectual turbulence, a subtle shift begins to take shape. Instead of treating the anomaly as a threat to established understanding, some start to view it as an invitation, a doorway into an era of discovery unlike any before. It becomes a focal point around which a new narrative coheres, one that portrays the early universe not as a predictable extension of current physical laws but as a dynamic field of possibilities that gradually cooled, stabilized, and narrowed into the orderly cosmos we inhabit today. In this emerging view, the anomaly is not an error but a message. The universe may have once allowed for forms of structure formation, energy distribution, and physical behavior that no longer occur. If so, the cosmos carries within its earliest light a fossil record of forgotten physics. This possibility ignites imaginations. Researchers begin crafting models that incorporate variable physical constants, temporary alterations in the behavior of gravity, and exotic early universe conditions that would accelerate growth without violating the conservation principles that underpin modern theory. These models are speculative, and their creators acknowledge this, but they also show how much room might exist in the unexplored edges of cosmology. Others propose entirely new mechanisms, interactions between fields yet undiscovered, transient states of matter that exist only at impossible energies, or symmetries that broke in unexpected sequences. The beauty of these proposals lies not only in their creativity but in how they underscore humanity's determination to push deeper into the unknown. Still, even as these ideas proliferate, a quiet tension persists. For all the excitement, there is an unspoken fear. What if the anomaly is pointing towards something fundamentally inaccessible to human comprehension? What if the universe, in its earliest epochs, operated according to principles that cannot be reconstructed or simulated because they belong to a reality no longer connected to ours? This fear does not paralyze the scientific community but hovers at the edges of their conversations like a shadow. It reminds them that the universe is under no obligation to reveal its secrets in ways that humans can grasp. Yet, paradoxically, this uncertainty motivates them even more. As the work continues, the anomaly becomes a character in its own right, a silent provocateur that challenges, inspires, and destabilizes. It disrupts careers and launches new ones. It forces revisions of textbooks and rewrites of lectures. It pushes the limits of instrumentation, theory, and imagination. The more scientists try to contain it within familiar boundaries, the more it slips beyond reach, urging them toward places they had not thought to explore. The anomaly's true power lies not in the data itself but in what it compels humanity to become. More curious, more adaptable, and more willing to accept that the universe is not a solved equation but an evolving story. By the time researchers step back to view the growing body of evidence as a whole, they sense that they are on the edge of something monumental. Not a tidy solution, not a final theory but a widening horizon. The anomaly stretches their understanding outward, deepening their appreciation of a cosmos that has always been stranger, more alive, and more unpredictable than their models dared to suggest. It reminds them that discovery is not a destination but a continual motion, a reaching, a questioning, a willingness to follow the faintest glimmers of truth even when they lead into darkness. What emerges from all this is not closure but momentum. The anomaly stands as a luminous signpost marking the boundary between what humanity knows and what it has yet to imagine. And though it complicates the story of the universe, it enriches it as well, transforming uncertainty into possibility and turning the cosmic dawn into a wellspring of endless fascination. In the quiet aftermath of humanity's latest confrontation with cosmic mystery, a new story begins to rise, one that feels less like a conclusion and more like the first breath of a deeper awakening. Scientists, philosophers, dreamers, and skeptics all find themselves standing on the precipice of an intellectual frontier where the familiar scaffolding of theory dissolves into something far more fluid, far more wondrous. The universe, as it turns out, is not merely stranger than imagination. It is an active participant in reshaping the very boundaries of what imagination can hold. In meeting the anomaly, humanity has glimpsed not a problem to solve, but a horizon that keeps moving with every step forward, as if inviting us into a dialogue older than stars. What makes this moment extraordinary is not just the data itself, but the collective shift in perception that follows. For decades, cosmology has pursued answers with the confidence of a discipline that believed the universe was largely understood, with only small gaps left to patch. Yet the early universe anomaly tears open a gap so vast that old assumptions fall through it effortlessly. The cosmos behaves like a story missing chapters, and the missing pages are not empty. They pulse with implications researchers can almost feel beneath their fingertips. Suddenly, the questions grow sharper, heavier, more poetic. Did the universe accelerate its own birth? Did unknown processes sculpt the first galaxies with motivations beyond physical law? Or is humanity misreading signals from an ancient epoch where the rules themselves were being forged in real time? In countless observatories, specialists gather around illuminated displays showing ancient light stretched across billions of years. Their eyes move across the images with a reverence normally reserved for sacred texts, aware that each pixel holds secrets from a cosmos that existed long before Earth's first oceans or the earliest flicker of biology. The galaxies revealed by the anomaly appear not primitive, but fully formed, grand structures brimming with order and complexity at a time when cosmic infancy should have permitted only rough sketches. It is as though the universe skipped steps, bypassing its own growth sequence, leaving behind questions as large as the void itself. And in confronting these questions, humanity confronts the limits of its own cosmic intuition. Outside the walls of research institutions, the public responds with a mixture of awe, curiosity, and existential reflection. People who never cared about astronomy suddenly find themselves entranced by the idea that the universe is rewriting its own introduction. Artists paint cosmic landscapes inspired by impossible galaxies. Writers craft stories blending science with myth. Even casual stargazers feel something shift inside them, as if the night sky has become more alive, more conscious, more intertwined with human destiny. It is a rare moment when an act of scientific discovery radiates outward like a cultural supernova, touching minds far beyond the laboratories that cultivated it. As debates intensify, the anomaly begins reshaping scientific language itself. Terms like formation, evolution, and expansion feel too narrow to describe what the early cosmos seems to have done. Researchers speak instead of emergence, orchestration, and cosmic intention, not in a mystical sense, but as metaphors that better capture the fluidity and boldness of the universe's earliest acts. It becomes clear that no single discipline can claim ownership of the mystery. Physicists need philosophers. Philosophers need mathematicians. Mathematicians need astrophysicists. And all of them need the kind of imagination that refuses to shrink in the face of the unknown. Late-night discussions at conferences take on a dreamlike quality. In dim hotel bars, Nobel laureates debate graduate students with surprising humility, acknowledging that the universe has humbled them all equally. They speak of variable physical laws, early universe symmetries that broke in unexpected sequences, or temporary conditions that may have permitted cosmic creativity at scales no longer possible today. Some wonder whether the anomaly suggests a universe that began not with a bang but with a bloom, a flowering of energy, matter, and structure far more intricate than any explosive model could describe. Others propose that the anomaly might be an echo from a previous cosmic cycle, a memory left over from a universe that folded into itself before giving rise to ours. Through all of this, a quiet truth begins to crystallize. The universe is not static. It evolves not only in form but in meaning. What it was billions of years ago is not what it is now, and what it will become remains an open question. A question shaped as much by future discoveries as by the minds willing to ask them. The anomaly thus becomes a symbol of cosmic possibility, a reminder that creation is not a fixed event but a continuous unfolding. Even now, stars ignite, galaxies drift, and dark energy whispers through empty space with intentions humanity has barely begun to decipher. As new telescopes prepare to launch, machines capable of lifting cosmic veils still untouched, anticipation ripples through the scientific world. Humanity stands at the threshold of instruments that may expose even older light, deeper patterns, or entirely new forms of cosmic structure. With each advancement, researchers brace themselves for further upheaval, aware that the anomaly may be only the first of many revelations waiting just beyond visibility. Some whisper that the universe might be preparing to tell a new story, one in which humanity plays a more significant role than previously imagined, not as observers, but as participants in the unfolding narrative of cosmic understanding. Yet beneath the swell of excitement lies a quieter, more intimate transformation. The anomaly rekindles a sensation long dormant in modern science: wonder. The kind of wonder that feels ancient, instinctual, almost sacred. An echo from the earliest humans who stared at the night sky with questions too large to name. It is the realization that, despite all our equations and instruments, the universe still possesses the power to astonish us without warning. And in that astonishment, we remember why we began searching in the first place. This revelation spreads beyond academia. Children stare longer at the stars. Teachers weave cosmic questions into their lessons. Filmmakers craft stories that blend speculative science with emotional truth. The anomaly does what no theory alone could do. It unites a fragmented world, however briefly, in collective contemplation of something larger than itself. It reminds humanity that the universe, vast, ancient, and indifferent, still offers a sense of belonging simply by allowing us to witness its unfolding drama. As the implications continue to ripple, researchers begin imagining what might come next. What if new data pushes the boundaries even further? What if the anomaly is only one thread in a tapestry of early universe phenomena we have yet to uncover? And what if the cosmos, in all its sprawling complexity, has only revealed the faintest outline of its true nature? These questions fuel new proposals, new missions, and new generations of scientists ready to venture into the unknown with courage sharpened by curiosity. In the end, the anomaly becomes more than a scientific puzzle. It becomes a companion, a silent guide urging humanity to expand not just its knowledge, but its imagination. The cosmos may be filled with mysteries we cannot yet decipher, but each one brings us closer to understanding our place within an ever-unfolding story. And as humanity prepares to step into the next chapter, one truth resonates above all: the universe does not merely challenge imagination, it teaches imagination how to grow.